Hi everyone. Today we will be talking about a very important problem in data science projects that you may face quite frequently, that is handling class imbalance. So, in this particular post, we will be talking about these points like what is class imbalance and why is it a problem while training machine learning models? What are the different matrices to consider and avoid if your dataset has class imbalance? Different techniques to handle class imbalance, and some algorithms around oversampling, that is SMART and ADASIN, undersampling, to make link nearest neighbors, and a combination of both, that is SMART plus to make or SMART plus nearest neighbors, alongside a final code sample that how these algorithms can be implemented in Python. So let's get started. So first of all, we will try to understand what is class imbalance. So basically, a very common issue at times in real world data sets. For example, you are going for a binary classification 1 0. In that case, class imbalance would exist when one of the groups, say 0, has a lot of entries while other has just a few. So, like for example, here you can see that a fraud detection system. If you're trying to spot a fraud transaction, for in case of banking, if you assume that is a positive class, say 1, amongst non-fraud ones, or the like the regular transactions that would be 0, the negative class, you may find that many non-fraudulent transactions would be happening as compared to fraudulent ones. So basically, if 1,000 non-fraud transactions are happening, so in that case, out of 1,000, only one would be a fraudulent transaction. So when you would be training a ML model over such a data set, it would be a big problem because the model has way more data on one of the class as compared to other. Eventually, while tuning the weights of the model, what will happen? Such algorithms will start favoring the bigger class and ignoring the smaller ones. So eventually, what will happen? There might be a case when your model will start outputting just a majority class always. Now, while dealing with class imbalance, some matrices can be quite misleading. So, if you have worked with any baseline classification problem, you might have used a metric called as accuracy. Now, in such a case, for example, the fraudulent transaction case that I'm talking about, assume that out of 1,000, just one of the transaction is fraudulent and remaining 999 are non-fraudulent. Now, in that case, the accuracy would be very high because if your model is outputting 0 for everything, eventually for 999 cases it would be correct and for just one case it would be incorrect. But the entire idea of building the machine learning model to detect a fraudulent system goes into vain because a model is not able to spot out the fraud transaction, which is the more important class. So that is why class imbalance is a problem. This becomes a bigger deal when the minority class, mostly the positive class, is something that you really care about. So like for example, if you are handling a data set around detecting rare diseases or say cancer, so out of millions of sample you would be getting just 2 or 3 positive samples. If you're not able to detect that, your building your machine learning model would go in vain. So this is why class imbalance is a big problem. Now we will be talking about metrics to avoid while considering class imbalance. So basically, if your dataset has imbalanced dataset, eventually accuracy would be the most misleading metric that you can have. And giving you the same example here, if you read, if 95% of the transactions are non-fraudulent, a model that always predict non-fraudulent, for example, it is always outputting you 0, will be 95% accurate but useless. Similar for error rate and mean squared error also. So mean squared error is basically for regression problems. So these are the metrics that you should be avoiding at all costs if you are handling a imbalanced data set. Now some of the recommended metrics that you should be following would be precision, recall, F1 score, area under precision recall curve, AUCPR. So you can read about these metrics. I think you would be already knowing about precision recall, F1 score. Focus of this particular post is around different techniques, how to handle class imbalance and eventually different algorithms. So there are three major techniques that you can follow. One is undersampling. So in undersampling, what we do, we are trying to reduce the number of instances in the majority class to balance the data set. So, like for example, if initially when we are starting off, we have 950 non-fraudulent and 50 fraudulent data set samples in the data set. So after undersampling, the final data set might look something like this: 50 non-fraudulent, 50 fraudulent. It is just an example. It can be more, so it won't be exactly 50. You can keep it 100 also. But basically, the idea is reducing the number of samples for the majority class. Similarly, for oversampling, what we would be doing, we would be replicating the minority class to match up with the quantity of the non-fraudulent or the majority class. So initially, if we are starting out with 950 non-fraudulent and 50 fraudulent samples, after oversampling, this may look something like this: 950 non-fraudulent, 950 fraudulent. So here you can see that we are increasing the total number of samples from 50 to 950. How is this done? I will be telling you the different algorithms that we have. Finally, something around a combination of the two that really goes well into the real world. So basically, we would be undersampling the majority, oversampling the minority, and then coming to a middle ground. So if initially we have 950 non-fraudulent and 50 fraudulent transaction samples, after using this mixed up approach, it can be 300 non-fraudulent and 300 fraudulent. So in non-fraudulent, we are doing undersampling, and for the fraudulent transaction, which are lesser in number, we are doing oversampling. So this is a combination of the two that can be used. So now we will be discussing about the different algorithms for each of the techniques like oversampling, undersampling, and the mix of the two, which we can use to perform them. So first of all, starting off with oversampling algorithms. So in this particular case, we will be discussing about SMOT and ADASIN. So SMOT is a very popular oversampling technique that you must have heard if you haven't used it already. So it stands for synthetic minority oversampling technique. So basically, a naive idea would be in oversampling to replicate the given data set, just repeat it. But that won't be an ideal case, because in that case, you are repeating, you are not providing variety to the model, and eventually the model may overfit on that data. So rather than just repeating the data set itself, we would try to generate some synthetic samples using the minority class samples that we already have. And in this, SMOT helps us a lot. It is a very popular algorithm. And now let's see how it works. So first of all, out of the entire minority samples that we have got, we need to randomly select one of the minority class instance. So this is for one sample generation that I'm talking about. Then we will be finding out its nearest neighbors from the same class. So for example, assume that we have picked up the random sample as this particular, the blue dot you can see. This is the, assume that this blue class is a minority class. Now, if we are picking up this blue sample, so we would be picking up its nearest k neighbors from the same class. So assume that k equals to 3. In that case, we would be picking up the nearest 3 samples. So that can be this, and this for this particular sample. I hope this is clear. So we are picking up the k nearest minority class samples and then generating synthetic samples. So what we would be doing, we would be randomly selecting one of the neighbors and create a synthetic samples by interpolating between the original instance and the neighbor. So if you see, assume that this is the origin, this is the sample that we picked. We picked up its 3k k nearest neighbors, and out of those also, I have randomly picked up this particular point. If you can see, now, how would we would be generating a new sample? We would be getting a point between, if we form a line between these 2 points, any point that would be falling onto this line, we would be consider it as a synthetic sample generated. So it's nothing, it's quite easy to understand. You pick up a sample from the minority class, get its k nearest neighbors from the same class, randomly pick one of the nearest neighbors, and then interpolate a point. Basically, a point on the line. If we create a line between these 2 points, which point will fall on that? We can pick one of them. So if we start off by say non-fraudulent transactions 950 and fraudulent transactions 50. So fraudulent is the minority class here. So this may look something like this. We choose a fraudulent transaction, transaction A. We find out its nearest neighbors, say B, C, and D are its nearest neighbors from the same class. We pick up a sample, random sample B for now to interpolate a point. As I told you, from the nearest neighbors also, we need to pick up a random point out of these three or four samples that are present. Assume that point transaction A has a value x1 y1 and transaction B has a value x2 y2, the points I'm talking about. So a synthetic transaction that we would be generating would have a value x1 plus alpha into x2 minus x1 and y1 plus alpha into y2 minus y1. Very easy to understand. So this would be the equation that we would be following. Where now, after applying SMOT, the final sample may look something like this. The fraudulent class would also become 950 with 50 points original and 900 synthetic. So we would be repeating the above step, like pick up a random point, get its k nearest neighbors, pick up a random k nearest neighbor, and then interpolate a point 900 times, and eventually we will be getting our synthetic samples. Not an extension to SMOT, we have got a algorithm called as ADASYN. So it is very similar to SMOT with a little difference. So as I told you earlier, in case of SMOT, what we are trying to achieve, we are doing randomly picking a class sample from the minority class in the initially, and then eventually picking out its k nearest neighbor. In case of ADASYN, the main focus is that certain points that are not in cluster with other minorities. So for example, if you look into this diagram, assume that this particular point, just follow my cursor, is also blue. So all the blue points are here, but one blue point is in the middle of the yellow ones. So in that case, what Adasan wants to say is that more weightage should be given to the point which is present in a seculated environment, which is not present with other minority classes, because such a sample would be the hardest to determine. So what we would be doing in this particular case, we would be assigning weights to each of the minority class samples that we have got, and then eventually, depending upon the weights, they would be picked up randomly, depending. So it's basically a weighted probability that we would be giving to pick up the minority sample, and then eventually rest of the process remains the same as for SMOT. So we pick up a point, weighted point, then we chose its k nearest neighbors, we pick up a random k nearest neighbor, and we interpolated the point. So the only difference between SMOT and ADASYN is how you pick up the first point, the random point that we are talking about from the minority class. In case of SMOT, it is random. In case of ADASYN, it is weighted. Now, how are these weights assigned? This is the most important part. So basically, it calculates the density distribution of the minority class samples. It is done by finding the ratio of majority class samples to the minority class samples amongst the k nearest neighbor of each minority class. A little tricky to understand. So basically, for example, if I pick up a point, say A, and k equals to 5. So I would be considering all the 5 points that are nearest to k and not just the minority ones. And then I will be calculating the ratio of majority class samples upon minority class samples. So this would be a little easy to understand. Assume that k equals to 7 in this case for point A, which has 2 minority classes and 5 majority classes. So the ratio would be 2.5. For point B, assume the minority is just 1 and 6 are majority in its k nearest neighbor. So the ratio would be 6. Now the weights can be assigned by normalizing these ratios, nothing else. So for point A, the weight would become zero point 0.3 because 2.5 upon 6 plus 2.5. 6 is this particular ratio, 2.5 is this ratio. And for B, the weight would become 0.7. So in this particular case, B would be given more weightage. So there are more chances that B would be picked up, and then eventually we would be interpolating more points from B as compared to A. Because this particular distribution suggests that B is in a seculated environment as compared to A. So this is how ADASYN works. The weights are assigned, and then eventually everything remains similar to SMOT. This is how both SMOT and ADASYN works for oversampling. There are many other algorithms that you can read about and eventually apply also, but these are the two major ones in oversampling for handling class imbalance datasets. So now in this section, we will be talking about undersampling algorithms, starting off with Tome's link. So do remember that one core difference between oversampling and undersampling algorithms is, in case of oversampling algorithms, we were trying to increase the samples of the minority class. But in case of undersampling, We are trying to reduce the number of samples for the majority class. So this is the core difference. Talking about to make sling, a very basic idea, not that complicated. Here we are trying to identify pairs of example that are very close to each other but from different classes. And once such pairs are identified, we would be removing the majority class samples from that particular pair so that only the minority class samples are remaining, so that the model doesn't get confused, because if 2 points are very close to each other, the model may get confused which label to assign if you have both the labels coming from. So this is the whole idea. First, look for pairs of examples that are close to each other. By close, I mean that the distance between them should be less, be it Euclidean, be it Manhattan, whatever distance you can calculate. For this, you can set up a threshold also. So for any point of pair of points, if the distance is less than say 2, they can be considered as a pair. Check their classes, and if they belong to different classes, remove the majority class. Now moving on to the next algorithm in this section, that is the nearest neighbor. Very similar to Tomek's link but with a minor difference. So in case of Tomek's link, we were trying to figure out pairs that are from different classes. In case of nearest neighbor, we are trying to figure out samples but from the majority class that are very similar to each other. So that we can reduce this information, we can remove redundant points, almost redundant points from the data set. Again, the idea is very simple. Identify the similar data points. It can be again following the same idea as in Tomek's link, where you can set up a threshold and remove less informative examples. Now moving on to the hybrid approach, that is oversampling plus undersampling. So there are multiple algorithms in this section also, which are very easy to understand because it is a combination of one oversampling or another undersampling algorithm. That's it. So one of the most important one is SMOT to make. So in this case, what we are doing, we would be applying SMOT to the minority class and to make link algorithm to the majority class. Similarly, you can use another combination also, Adasin plus Tomeg, etc. As told, these are the most important section, and I think in real world they would be the most helpful one, because at any point of time you would wish to have a mix of both, oversampling and undersampling. Now, moving towards the last section of this particular post, how these algorithms can be implemented. So for that, we already have a pretty good library in Python called as imbalanced-learn. So you can just pip install it, and the sample code is very easy to understand. I think these I'm making a dummy data set here, so that is why I make classification, splitting the data set. I think this is not relevant to implementation. So the changes that you are bringing in a normal pipeline would be, you would be importing this particular line, as you can see. This implementation is for SMOT, but for other algorithms also the implementation is same. You just need to change the import name. For example, in place of SMOT, it can be Adasin, and if you're importing over undersampling example algorithms, it can be under underscore sampling import say tomixling. You just need to read out the documentation a little. Here you are creating an instance of smart and then calling smart.fit underscore resample. That's it over the training data set. So you can see that we started off with 7,000 samples for 0 and 800 samples for 1. After applying smart, both the sample size have now equal in the data set and making it a balanced one. So this is how class imbalanced can be negated. This is what class imbalance all about. These are the different algorithms and how IMB balanced learner library can be used for implementing these algorithms that we have.